Okay, so let's get rolling, go over the homework for today, and then start talking about strings and manipulating strings. All right, so for homework 3, we were practicing with loops and things like that, building on top of our conditionals and Boolean expressions. So let's just start putting this stuff in. So we're supposed to define a Boolean variable named isRainy and set it to true. So let's get into our, let me. Do that. Okay. All right, so we're creating a Boolean variable named isRainy, and we want to start it off as true. Next, write an if statement that checks if it's rainy, and if it is, print bring an umbrella. All right, so kind of repeat from last time. So if is rainy, see out, bring an umbrella. Something like that. All right, right now is rainy is true. So when I run this, I should see bring an umbrella. There's my bring an umbrella. If I were to flip this guy to false, now I won't see that as output. I see no output. Remember, all programs begin and end with main. So main starts here, defines a variable. That variable is equal to false. We ask a question. Since this guy boils down to false, we do not execute this statement here. We end up hitting the end of the program down here. All right. So we're going to throw a else clause on there saying enjoy the sunshine. And that's what's going to happen if rainy is false. So we'll throw an else on this guy. Right now, since it's false, we'll get the enjoy the sunshine. So there's that guy. Keep trucking along. Next part, Boolean expressions and multiple else clauses. This is what we talked about last time with the else ifs and things like that. So define two integer variables, an x and a y, and assign them any value. So let's create a couple of integers. Int x is equal to 5, int y is equal to 10. Start off with that. Write an if-else structure that prints x is greater than y if x is greater than y. So we'll ask the question, if x greater than y, see out x is greater than y. Else if x is equal to y, so if x is equivalent to y, double equal sign, not single equal sign, double equal sign. So if it's equivalent to y, we will output x is equal to y. Lastly, if x is less than y, now this is the only other case that can be in existence, right? It's either greater than y, it's the same, or it must be less if we're still kicking. So we would throw this guy inside of an else, not necessarily another else if. An else if is not necessarily incorrect. It's just not needed in this place. So if I say else, like that, that's the same thing as throwing in an else if x is greater than, what's it, x is less than y. But that's the only other possible case, so we would probably leave that as an else. And remember last time we talked about this kind of weird syntax here with the else if? Technically, because I've mentioned that you should always use curly braces, it's never wrong to use curly braces. So technically, this should probably look like that by following my rule. Nobody would write it that way. They would always do the else if without the curly braces. I don't know, take it as I don't know, best practices or something, but both of them mean the identical thing. All right. Now, one thing I have noticed as I was kind of looking through the homework assignments, and this is common for beginning programmers, it's you get a little verbose with your curly braces. I'll get things like, you know, a curly brace here and another curly brace in here. Sometimes you'll wrap these things in curly braces, that kind of stuff. Kind of the when in doubt, throw a curly brace in there. All right. And what's call it unfortunate about this is it's not an error, right? You're getting the correct output. Why is that? When you have an opening and closing curly brace, what kind of statement is that? We've talked about it in context with a if or a loop. It's a block statement. And a block statement is opening curly brace, closing curly brace, and then 0 or more statements on the inside. Which means that technically, for example, this line right here, which is extra weird, the curly brace followed by defining a variable followed by a closing curly brace, this whole line is a statement that contains exactly one statement. That's not illegal code. It's just weird looking. All right. So you would not put curly braces there in really any circumstance. So you only need curly braces in situations where you are specifying that you want all this stuff to be part of kind of a boss. Where right now our possible bosses are if statements or loops. We're going to be throwing in functions, even though you technically already have a function with main that we just happen to always write the opening and closing curly braces for, but we really haven't gone into that detail. We'll be talking about functions here pretty soon. But you would only use the opening and closing curly braces when it's part of a collection of things you want to do as a result of something else, even though it's not syntactically incorrect. Okay, so something to keep an eye on. Also, I mentioned this before, it's also common for beginning programmers to do things like not indent. So you'd have code that kind of looks like that. Also, not incorrect. C++ doesn't care if you put your entire program all on one line. Okay. You want to get out of the habit of doing this. You want your code to look well organized and look properly indented. That will make your life easier later on when you start having programs that are not 10 lines long, but are instead 500 lines long. And if things look like what would usually be called spaghetti code, just kind of all over the place, it's going to be very hard for you to debug things when you get your 4,000 errors. Okay, so try to pay extra attention to indenting this stuff. Just hit tab a couple times. Make it look good. Again, I'm not taking points off for it. It's not actually incorrect, but it's going to come back to haunt you later. It's a good time now to practice those things because things are going to keep getting more and more complex. You might as well get this practice now rather than have to deal with new complex stuff and then also be running into these problems. All right, so there's that.
Hey, Professor,
What's up?
uh, could you let Jamil in from the waiting room?
Oh, thank you. Done. Okay. So next one. So that's this thing we just wrote using Boolean expressions in loops. So we're going to define an integer variable named counter and set it to 0. Then we're going to create a while loop that continues as long as counter is less than 5. And inside the loop, we're going to print the value of counter and then also increment it by 1. All right. So we'll say int. Let me just get this higher up on the screen. Counter is 0 while, actually it's called counter, right? While counter is less than 5, what do we want to do? We want to print out the current value of counter. And then also set counter equal to whatever it's currently equal to plus 1. All right. So again, define a variable, ask our question. Is this guy less than 5? Is 0 less than 5? It is. What do? We print out 0. 0 becomes 1. Spin back up. 1 less than 5? Yep. Print out 1. 1 becomes 2. 2 less than 5, 3 less than 5, so on and so forth. Go ahead.
So does count mean like the same thing as counter? Because when I
You can name it LOL. These are just variable names. We're just defining a variable here.
so it just like helps us in the long run, basically.
Well, you should have a variable name that's meaningful. In this case, we're writing a loop that's going to do some counting. So we called it counter. All right, but it's not like a built-in thing. All right, I'll go ahead and run that real quick just so we can throw our expectation in here. We didn't run this up here, I don't think. So we have X and Y. X is 5. Y is 10. Is 5 greater than 10? Nope. Is 5 equal to 10? Nope. So this is going to get caught up in the else. This is going to print out X is less than Y. And then we'll have our loop here, which is going to print out a 0, a 1, a 2, a 3, a 4, but not the 5, right? Because it's going to go as long as counter is less than 5. So there's our X is less than Y, and there's our 0 to 4. Go ahead.
How come but the X is less than and after the else?
What do you
like
mean?
you did with the else.
Oh, you mean, why didn't I say this?
Yeah.
Else X is less than Y?
Yeah.
You could. You'll get the identical output.
Oh, okay.
Okay. Oh, this has to be an else if, like that.
Oh, okay.
All right. But nobody would probably write it this way. All right. And the reason being is
Just because it's
if,
already up there.
well, that's the only other possibility.
Okay.
X is either greater than Y, it's the same as Y. And if both of those have failed, I kind of look at this as like a minefield.
Yeah.
Okay. If we're still kicking down here, the only reason we're still alive is that because X is less than Y.
Okay.
Okay. Okay. And remember, inside of an if statement, inside of an if else kind of block, you will only get into one of those. There is not a possibility of landing in more than one. Okay. So I would, here, just for the sake of your documentation, I'll put a little comment there. Okay, so remember, double front slash means that you want the compiler to ignore that code, but for human eyes. So I'm kind of showing you here that if you wanted to throw that Boolean expression in there because it made you feel better, that's fine. I'd rather you get it right and understand it than have either the wrong solution or a solution you don't understand, even if you're getting the right answer. All right, so there's our while loop. Then our do while loop, remember the difference between while loops and do while loops is do while loops are what are called post check loops, which means we will execute the body of the loop at least one time, regardless of what the Boolean expression is. Whereas with a while loop, we check that Boolean expression the very first time, which means we may not get into the body of the loop ever. I'm just showing you an example of that real quick. If we set counter to 50 to begin with, is 50 less than 5? Nope. So we will do absolutely none of that. We never get inside that loop. Make some sense? We are checking that Boolean expression ahead of time. But if we had this exact same thing written as a do while loop, it would print out 50 and then die on the second pass. Okay. Let's see, what did they want us to do? Use a do while loop to accomplish the same task as above. Print the value of counter and increment it as long as it's less than 5. Okay, and this is actually a good example because I have already created a variable named counter, right? You cannot redefine a variable with the same name inside of what's called the same scope. We'll talk about scope in more detail later, but for now, scope is where do I have access to this variable? All right. So for us right here, counter is accessible from line 41 on inside of main. We'll spend plenty of time talking about scope, so don't go into the weeds with that too much right now. But basically, when I get to this line right here, if I want to keep using counter, that's not a problem, but I do not redefine it. I can go back and say counter starts off at 0 again without redefining it. Then I would say do some stuff. What am I going to do? I'll print it out and I'll increment it. How long am I going to do that? I'm going to do it as long as counter is less than 5. And then statements end in a semicolon, which is why we have that semicolon there. Unless it's a block structure, and then there's no semicolon. All right. So up here, I first defined counter, started it as 50. We asked the question, is counter less than 5? Nope. So since this is false right from the get-go, we will fall past all this code and do none of that. Then I'm setting counter to 0. I'm not redefining it. I'm not building a brand new variable. I'm using an existing variable and just changing the value that was in there that used to be 50. I'm changing it back to a 0. Then what am I going to do? I'm going to output the current value of counter, which is 0. Then I'm going to increment it. 0 becomes 1. Then I'll ask the question, is 1 less than 5? Yes, it is. So this will do that 0 through 4 thingy. There's my 0 through 4 thingy. Now, like I talked about a second ago, if I can set it to 50 here if I want, just so it's really reinforced, but we know it was already 50 when we got to that line. All right, so this is redundant, but I'll just set it there right before our example for this do while loop. So counter is 50. A do while loop is a post check loop, so it does not check that Boolean expression until after we've gone through the body of the loop one time. So it's going to print out 50. 50 becomes 51. Is 51 less than 5? Nope. It'll move past. So we are going to get a 50 out of this. There's our 50. All right. And then a for loop. Use a for loop to achieve the same task as above. Print the value of a counter from 0 to 4. Now, this is actually going to be an interesting thing. So I'm going to say for int counter is equal to 0. Counter is less than 5. Counter is equal to counter plus 1. So remember, a for loop kind of grabs the parts of a while loop and drags it into the header of it. All right. So I've created a variable called counter. Now, the first thing you should be wondering is, wait a minute, didn't he just say that we don't need to redefine counter here since it already exists up here? That's a true statement. I didn't have to redefine it. I could just say counter starts off at 0. And I can run it. Then the question is why did that work? Why is it not incorrect if I just say counter equals 0 there versus defining counter to be equal 0? We expected this guy to give us an error because if before this for loop, if I said int counter is equal to 4, and then I try to run it, it's going to yell at us. It's going to say redeclaration of a variable called counter. So it didn't like it. It saw, hey, you defined counter up there. You don't have to define it again here. But it seemed to be completely cool with me defining it right there. Trying to run. Give it a moment. Copy the code just in case. There we go. Okay. No error. It was cool with that. So the question is why? This kind of goes back to the thing is always understand the code you wrote, even if you're getting the right answer. If you don't know why you're getting the right answer, you should explore it. Go ahead. Yep, it's not almost. For loop creates its own scope. So I'm going to write a slide here with a true statement in it. We're going to say all variables resolve to their most local scope. And what does that mean? If we look at our code right now, we have this global scope that is everything. So if I define some stuff up here, if I say int blah equals 4, this guy is accessible anywhere inside this file from line 12 on. Okay, it is a global variable available to everything inside this file. Now, if I go inside of main and I say int blah, let's both just say blah2 is equal to 4. Blah2 is a local variable inside of the scope that is owned by the function called main. So I have the global scope, and then what lives inside of that global scope is another scope called main. And the stuff that's defined inside of main are only available from that point forward until main ends. As soon as main is over, we know all programs begin and end with main. Program's over. But if you let your imagination wander for a second, and we're going to be creating our own functions here pretty soon, our own functions just won't be named main, but they'll be named something else. So any variables we create inside of those functions will disappear on us as soon as the function is done. All right, because they have their own little scope. And as he pointed out, we have another scope here that lives within main, and that's the scope that is part of this for loop. So this is a scope within a scope, within a scope. We have the global scope. What lives in that is the main scope, and what lives inside the main scope is the fat for loop scope. Every for loop gets their own scope. Now, the way the language is actually written under the hood, that for loop scope is kind of an entry level scope. It doesn't necessarily get all of the benefits when we run into some stuff that a difference does occur. I'll point it out. But for all intents and purposes, 99% of the time, it behaves like a normal scope. So when we talk about a variable and we're using that variable, all variables will resolve to the value found in the most local scope for that variable. What this also means is when we try to resolve a variable, we look at the local scope first and then expand our search from there. You can think about this like if you've lost your car keys and you're in your living room, you would probably search for your car keys in the living room first. Then you would expand your search to the kitchen, to other rooms, other scopes. Make sense? And if you've checked everywhere, then you just assume your car keys are gone or stolen or whatever. If you checked everywhere you have access to. So getting back to my question of why is this okay? When defining that variable before here again was not okay. Remember it screamed at us? Inside of main here, I already have a variable named counter. So when I try to define another variable named counter also inside of main, it said, hey, you already have a variable in this scope named counter. You can't define it again. You could use it again, just don't redefine it. Just put a new value in there and move on with life. Okay. But it did not yell at us when we did it in the for loop, because this creates an even more local scope. So in this case, counter equals 0. When I see out counter here, this variable resolves to its most local scope, which is the definition of counter right there. If I choose not to redefine counter in that for loop, instead I just I just update its value. In this case, when I'm using the variable name counter right here, I'm not redefining it. I'm not putting the type in front of it. I'm utilizing a variable that already exists. So again, all variables resolve to their most local definition. So when the program tries to find the current value of counter, it's going to look on the floor locally and it's not going to find one because there is no variable called counter that was defined inside the for loop. And then as soon as it fails on that search, it's not going to give up yet. It's going to jump up one level and it's going to look inside of main and see, you did have a variable named counter right here. So when I wrote counter equals 0 there, I am overwriting this version of counter with the number 0. When I print out counter right here, again, it's going to look locally in the for loop. It's going to see that there is not a locally defined variable named counter. So it's going to jump to the next most local scope and it's going to find my value of counter from main. All right. And I can show you I'm going to show you a little cheat thing to show you what I mean by that. I'm going to show you a pointer, but we're not talking about pointers yet. All right. So what I'm going to do right before this loop is I'm going to see out and then inside that loop, I'm going to do the same thing. All right. So for right now, we see that I did not redefine the variable counter inside the for loop, right? So I'm using that same original counter variable that was defined inside of main. When I run this, notice that this value and this value are the same value. Make some sense? A pointer is a memory address. So I'm showing you the scary hexadecimal value. So when so this is counter in the for loop and counter outside the for loop is pointing to the same place in memory. Whereas if I decide to create my own more local version of counter here, all I did is define it instead of use the old one. And then I run this. Oh, it is using the same address. That is weird. Remember when I said earlier that it's kind of a low end scope? It's not, the for loop isn't quite the same scope. What I expected, let me do something else here. Int counter I won't be able to do that. Oh, it's because I'm not getting into I am getting into the loop. So counter is at 50 there. We drop past that. I'm outputting the value of counter, but this little ampersand says, give me the address of that variable, where it lives in memory. So I'm outputting where that guy lives in memory. Then we get to the for loop. I'm redefining counter right here. I'm then outputting the address of counter inside this for loop. I mentioned that all variables resolve to their most local definition. So this version of counter should resolve to this guy right here, which is a brand new version of counter. But when we ran it, we just saw that, in fact, it actually is not a brand new version of counter. It actually lives in the same memory location. Good.
Can you make it a long set of?
I actually might, because then it won't flow through because it is a different type. Nope, it's location of the variable name. Didn't make a difference. So at some point when it'll be soon. When we go and do functions, I'll show you a second function with two variables with the same name. There'll be different memory addresses. Go ahead. Oh, thank you. Okay, so let's go back and let's revisit. All right, so right now, here, I'm gonna do this. Inside for loop. I'm gonna label it. And then we'll write outside for loop here, because it is printing it multiple times. All right. Now we'll run it. So in this case, I did not define a brand new version of this. So inside the for loop, we have, as he pointed, I wasn't scrolling up. So we have all of the same variable names. Outside the for loop, or all the same variable locations. Outside the for loop, we also have the same variable location because we did not redefine the variable. This version of counter resolves to its most local definition, which is the same version that this guy's using right here. But if I redefine this guy, giving myself a more local version, that's E58 there inside, and that's E54. Thank you. So these are different memory addresses because I have created a new variable that is more local. But what I still said earlier is still true, that the for loop scope is kind of a mini scope. It's not quite, doesn't quite have all the features of a full-fledged variable scope. And that'll make sense when we talk about it much longer, much further down the line. It has more to do with how it's implemented under the hood. All right. Now, at this point, you can pretend like I didn't show you the syntax yet because we're not talking about pointers yet. I just wanted to show you that little memory addressy thing. This kind of goes to our conversation we had maybe last week or the week before about that addresses and computers are easy. All the things live on one big long street, as opposed to human versions of addresses where you have a house number, a street name, a city, state, zip, yada, yada, yada. Much, much more complicated. But as soon as you start seeing stuff that looks like that, it starts getting intimidating because those are scary looking, these big hexadecimal values. All right. So there's our for loop that's doing the same thing. Remember, a for loop has its own scope. All these pieces are self-contained inside of here. I'm going to write this a little bit differently just to show a point here. So I'm going to say int I is equal to 0. I is less than 5. I is equal to I plus 1. I would say I, J, and K are very common counting variable names for for loops. Typically, when we're using a for loop, and a for loop, I mentioned last time, it kind of lends itself to counting type problems. Do something so many times. Usually the variables you're using are kind of throwaway variables, where you wouldn't necessarily have a big use for it later on. So you might not necessarily want to type a 9-character variable name out or something like that. And typically we have 3 different ones, I, J, and K, which are the common one used in for loops, because within normal problem solving, the most you'll have is a loop inside of a loop inside of a loop. That kind of allows you to deal with things in three dimensions. And we'll see an example of that at some point, but that's why it's just I, J, and K. But that's not required. You can name them whatever you want. All right, so I'm going to get rid of this pointer stuff because we're not ready to actually talk about that yet. So now this is a for loop that does the same thing as we were doing before. Start I off at 0. Keep going as long as I is less than 5. It is a pre-check loop, just like while loops, as opposed to a post-check loop like a do while loop. So since this is true, we'll execute the body of the loop, and then at the end, we update the variable. So this will print out a 0 to a 4. There's our 0 to the 4. All right. So it looks like that's the homework assignment. So I'll go ahead and save that. What was this, homework 3? Share the code. Oh. Where is there? There we go. All right. Any questions about the stuff we just did before I continue on? Not related to pointers yet. You can pretend like I didn't show you the pointers. Soon enough. All right. So the next thing we want to talk about is we're going to introduce another variable type. All right, so variable scope, I've given you kind of an intro definition for this. We'll continue to build on that, but for right now, it's just where do we have access to this variable? Last thing I was going to show you, I forgot about it. If I throw that line in there, what's going to happen right here? What do you expect to happen before I run the program? The question that deals with variable scope. I was defined inside the for loop. It belongs to the for loop. When this for loop ended right here, and I got to this line, I no longer exists. When I run this, it's going to scream at me and say, hey, I don't know about any variable named I. Well, why not? I said all variables resolve to their most local definition. From line 64's perspective, the most local scope is the scope controlled by main. He doesn't know about the scope of that for loop. Scope of the for loop has already been born and died by the time we get to line 64. It's out of his reach. So he's just going to check the scope associated with main, and if he doesn't find it there, he'll check the global scope that's outside of main, like this blah variable. So if I threw an I up there, now it'll print it out. So it knows about I again. Checked in main, didn't find it there, checked the global scope, did find it there. All right. So that's kind of a good exercise to mess with. And I would encourage you before you ever hit the run button to ask yourself, what do I expect this code to do? Don't use the run button as a trial and error device. Now, if you don't know what to expect, you're like, okay, well, let's just see what happens. Well, as long as you're doing that on purpose, that's fine. But try not to rely on the run button because it's going to be a good exercise for you to look at your code and be able to interpret what's this guy supposed to do. So in this case, I got rid of my variable I up here. So I is not defined. I was defined in the for loop. It died at the end of the for loop. So when I got to line 63 right here and I tried to access the value of I, it's going to say, I've never heard of that guy. You never defined a variable named I. All right. So now let's talk about another variable type. All right. It's a lowercase s for string. So at this point, we've just messed around with the primitive type variables, the short, int, long, bool, char, float, double, those guys. So now we're going to add one more character, one more thing to the list, and that is the string data type. Now, strings are very interesting in C++ because it's a good way of looking at how C++ has evolved over the years. If we go back to the early days of C++, a string was actually represented as a collection of chars in something called a character array. We'll be talking about arrays before too long, but that has limitations associated with it. Then there was something called the standard template library that came out years and years later that had a whole bunch of stuff built into it that made the life of a C++ programmer easier. So they had a thing in there called a C string, kind of a little bit more friendly version of a string, and it had a whole library of stuff that could operate on those strings. Well, then after we got some of these newer languages like Java and C#, I'll often refer to Java as a string-based language. If you have a value stored inside of a variable of type string, you can do almost anything with it in Java. You can convert it to whatever you want, so on and so forth. All right. So the string version we're going to look at here in C++ is kind of the one that is the most recent addition to C++. So it's the one that has it behaves the closest to the strings you'll be working with in our more modern languages. All right. So if you've never programmed before, you can just forget what I just said. But if you've programmed before and you've done something with C and C++ and you've used old style strings like a char pointer, s is equal to hello, something like that, we're not doing that in here. We're going to say string s is equal to hello. These are very much a modern version of a string. All right, so strings are double quote followed by a collection of 0 or more chars, followed by a closing double quote. That's what a string data type looks like. And where do we store string data types? We store them inside of variables capable of holding strings. So if I go back out here, let's just gut this whole thing. You already have my saved version that I put up there. So I'm going to go ahead and say string s is equal to hello. And then I'll say cout s. You see we have the output hello. Similarly, we can say cout, we'll prompt the user, enter your name. And then we'll say string name is equal to cin. I actually got to write this in 2 lines for this guy. Yeah. All right, so I'm going to prompt the user to enter their name. I'm going to create a variable named name of type string. I'm going to use cin to read in from the user whatever they type into that variable called name. And then I'll print out name proving we read it in. So this is just reinforcing that whole user IO thingy we talked about last class. Or class before that, whatever it was. All right, so there's my hello. Now let's enter your name. I'll type in Mike. Did I type down here? Oh, I did. It was just slow. Press enter, and it read it into this variable called name, and then I echoed it back out by saying cout name. So it showed me it was able to read that in. Make some sense? So again, another use of cin. We can read, it reads into whatever type. Any of the primitive types as well as strings. Outside of that, other types we might create inside of this language, cin will not work for. And we'll run into examples of that. So really, in most modern programming languages, the string data type really behaves like a primitive type most of the time. It behaves as a type built into the language. But there is a difference there. So we're going to say behaves mostly like a primitive type that is built into the language. But it also has abilities that come in the form of functions that differentiate it from primitive types. So all of our primitive types like ints and chars and bools, those guys, if we want to do things to them, for instance, if I want to convert a, let's see what would be let's say I want to take an integer to a power, something like the third power or something like that. We would have to use an external function that would take in the integer I want to take to a power as well as the power I want to take it to, and it would internally do the magic to make it happen. And we'll probably write that function ourselves here relatively soon. All right, but you need external entities in order to operate on primitive variable types. Strings have some built-in features, built-in bells and whistles. So for example, strings can report their length. So I can say cout name.length type in Mike again. So I expect that to have a length of 4. There is the number of characters that live in Mike. All right. Now, just for testing purposes here, I'm going to go ahead and hard code Mike into that variable name, and then I'll comment out those lines. That way I don't have to keep prompting myself and typing it in. So here's a single line comment. Here's a multi-line comment. All right. So I'll go ahead and output name.length. We'll see this has a value 4. Okay. Now I'm going to also output cout name at position 2. We see we get the K. All right, so let me show you what's actually going on there. Call this guy string storage. Draw a couple of pictures here. Killing me. Just let me type it lowercase. I'm just leaving it. All right. Well, let me do that one. There we go. All right. So we have a variable. When I say string name is equal to Mike, like that, what it's going to do is it's going to create a variable called name. And that variable is going to point to a place in memory where these 4 chars are stored. Steal this guy. Change this to make those green. This is 0. This is 1. This is 2. This is 3. All right. So there are 4 characters in this string, as we saw. I'll put it right here. And when I outputted the character that lives at bucket 2 of that string, position 2, index 2, I'll often call it bucket 2. It went and looked at that string, went to bucket 2, and found the K. Strings, as our arrays, when we talk to them, are 0 indexed. So if something has 4 things in it, it's indexed 0 to 3. All right. Now, just to kind of throw a little bit of that memory pointer conversation here, even though we're not really covering it yet, I'm going to throw another row up above here because there's actually 3 things going on. All right, and I'm going to do this as 100, 101, 102, 103. I just want to test something here real quick. Make sure I had mentioned that chars are 8-bit values in C++ because they use the ASCII character set instead of Unicode. Let me just make sure that that's the case in this guy. Actually, I would just do size of char. I didn't even need the variable. So I'm expecting this to give me either a 1 or 8 for bytes. A 1. So it's 1 byte. So what I advertise is correct. So the size of a char in C++ is 1 byte or 8 bits. And that's because the ASCII character set has 256 unique characters in it, as opposed to Java and C#, more modern languages use the Unicode character set, which has 65,536 unique characters in it. Not a problem for us, but it's a reality. And it'll also make this slide accurate. So I'm making the assumption that when I first created this variable, string name is equal to Mike, I'm assuming that memory was created at location 100 in RAM. with enough additional memory to store the rest of the string. So in this case, I was going to store 4 characters. So we asked our operating system, go and find me enough memory to hold 4 chars. We just saw 4 chars is, well, 1 char is 1 byte big. So 4 chars would be 4 bytes big. So we were asking our operating system, go find me a plot of land big enough to hold 4 bytes next to each other, hold contiguous memory. All right. Don't have to worry about how it accomplished that. That's just that's the ninja move that happened behind the scenes. Go and find me memory. The operating system did the magic for you. All right. And the reason we're not going too much into it right now is with strings, it's difficult to get at that memory address. When we get to arrays like an integer array, I'll be able to show it to you in more detail. So don't worry too much about that. I'm kind of explaining the stack of 3 things here. So I'm making the assumption in this example that after I created this variable called name and the program went and talked to the operating system and asked it to find it enough memory for 4 bytes to hold my string, it came back and said, I found you a nice soft plot of land and memory address 100, which is a much less scary thing than a giant hexadecimal value. All right. So it found enough land at memory address 100 to hold 4 chars. The first one lives at 100. The second one lives at 101. The third one lives at 102 and 103. These are all memory addresses. Why? Because this char is 1 byte big. 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 And these guys are indexed 0, 1, 2, and 3. Now, the reality is, let's call it 99.99% of the time, in your program, you actually don't care about this 100, 101, 102 thing. This is just kind of showing you what's actually happening under the hood. But you do want to have a way of getting at certain characters in a string. And we do that with this syntax right here, where we have the name of the variable, followed by an open square bracket, followed by a legal index, followed by a closing square bracket. This says, give me bucket 2 from this string. And bucket 2 in that string is a K. If I change that to bucket 1, it'll be an I. If I change it to bucket 7, it didn't scream at me. This is a differentiating thing between the newer style C++ strings and our modern strings that live in things like Python, Java, C#. If we were working in Java here and I tried to access bucket 7 of something that only had 4 buckets in it, it would have screamed at me. It would have said array index out of bounds exception. Okay. In C++, which still opens up the world of our system's memory to us, says, hey, you want bucket 7? No problem. What's actually happening when I say, give me bucket 7? Well, let's look at what's actually happening when I say, give me bucket 2 first. So if I say name at position 2, what this guy is actually doing is it's saying, go to the base address of name and add to that 2 times the size of a char. Now, we already saw that the size of a char is 1 byte. Base address of name is 100. So that's 100 plus 2 times 1, which is equal to 102. Bucket 2 lives at memory address 102. Make sense? So the actual value that lives in my variable called name is not the string. The value that lives in name here, going through my example, is actually the number 100. It's the memory address where you can find that collection of chars inside of memory. Now, because C++ is a strongly typed language, and if we define something as a string, C++ knows that, hey, even though it actually is holding a memory address, I'll go ahead and take care of all the lookups and stuff for you, so the programmer can be convenient. You know, the quality of life is better. So you don't actually have to worry about your string holding this memory address. I'm just telling you that's what it actually holds. So when you go to print out name, it's going to go to this starting address and start printing out one character at a time. All right. So what happened when I said name at bucket 7? Well, it did the same exact math here. Base address of name is 100. In my example, I just made up the number 100. I pretended like I was the operating system, and that was the memory address I assigned to give us a simple number that we can count with. 100 plus 7 times 1 is 107, right? Now I'm telling you that is a real memory address. It's not a memory address we asked the operating system for. It's not one it assigned to us, but it's a real place. So effectively what we just did is we wandered into our neighbor's yard and we printed out what we found there. Just so happens our program is running inside of this kind of a virtual container, kind of keeping it, protecting the memory that's in there from bleeding out into your external applications. This is something that's happened over the years since early C and C++ programs first came out. In the early days as a C and C++ programmer, you could walk off the end of a string or an array. This was something called a buffer overflow error. You maybe have heard of that before with when you hear people talking about hackers doing something with your web browser to get your credit card or tack something on into memory. What it's doing is it's using this little trick to get into your computer's memory by walking off the end of something that already exists. Now our modern programs are protected from this. The operating system runs your C++ program inside of a little bubble. All right. And all the memory that you're using belongs to that bubble. So all that memory is empty right now anyways. It just happens to be memory that was allocated for your program, even though you haven't requested it yet. So when I say I want to go to bucket 7, it's just doing the identical math that it did for getting me to bucket 2 or getting me to bucket 0. It's saying, hey, I'm going to go to the very beginning of that string and I'm going to take 7 char size steps through memory and I'm going to tell you what I found there. And since we're inside of that allocated memory for our program and nobody else had access to it, what we saw there is nothing. Not an error. It just showed me that there is nothing at that memory location. In a more modern language, it would have recognized that, hey, you are accessing bucket 7 of something that does not have that many buckets. And it would have screamed at us.
I have a statement.
Say this again, I'm sorry.
I said I have a statement.
Go ahead.
So in Java, instead of it being nothing, it would just scream at us saying the string out of bounds exception, the string index out of bounds exception.
Correct. But the way it works behind the scenes is identical. So this math I'm showing you here, when I say name at bucket 7 or name at bucket 2, Java works the identical way. The only difference is Java has a little bouncer standing at the edge of your yard, and he screams if somebody walks into the neighbor's yard. Where C++ doesn't do that. Which is another reason why I pick C++ as our first language, because there's less hand-holding. It allows you to wander into your neighbor's yard and get weird results. Okay, you'll learn pretty quick that you don't like weird results. Java protects you from that happening, which, you know, you probably still learn it okay anyways, but it's more fun to watch you squirm when you get bad errors and have no idea why. But that's why I'm showing you the under the hood stuff. Okay. So if I wanted to display all the characters in this string, I have a way of getting the number of characters in my string, right? By using its length. I have a way of getting a character from a particular element, particular position, particular bucket in my string. So if I have a string name here, couldn't I write a loop for int I is equal to what is the very first legal position in a string? Always. Here's our picture. What is the very first legal position in our string? Every single time it's a 0, right? So I want to start at the very beginning of my string. I want to keep going until I reach the end of my string. What is the last legal position inside of a string called name? How can you express to me accurately what the last legal position in a string called name? You don't necessarily know that name holds the character's mic right now. It holds something. There's a variable called name. What is the position of the last character inside that variable?
You're asking like what method you use to get this like all this stuff.
So here's our example of Mike. The last legal position in this guy is 3, right? Is there another way you could tell me about 3 without knowing that Mike had 4 characters in it?
Dot length.
Length minus 1. All right, so the length of a string minus 1 is the location of the last legal element in that string. Because strings are indexed by, or 0 indexed. Go ahead.
So what do you mean by length? Is that like the amount of characters typed, or is that?
No, it's the number of characters that are in there. So let me take this out for a second. So if I say cout name, which is the name of my variable, dot length. So in this case, I'm saying I want C++ to report to me the length of that string, the number of characters that are in that string. In this case, name holds the string Mike. This will print out a 4. There's our 4. If I change this to elephant, now it'll print out an 8. Number of characters in that string. So I'm going to start off I at 0, keep going as long as I is less than name dot length. And notice that length, I have an opening and closing parenthesis at the end of it. That means length is something called a function. We'll talk about functions here probably next class, but right now that's just the syntax for it, the magical syntax. Okay. Now, why am I saying less than name.length instead of less than name.length minus 1? 0 indexed. The last legal bucket is length minus 1, which means I'm going to keep going as long as I is less than the length. I could say I is less than or equal to the length minus 1 if I want. That'll mean the same thing. But our stock for loop for walking through a string
I have a question.
is that guy right there. Go ahead.
Why don't you just use I plus plus? Why you don't want us to do
Yeah,
that?
I mentioned that last class. I'm going to introduce the plus plus operator. I've just not introduced it yet.
No.
There's more to it than most people think there is. I plus
Okay.
plus is not as trivial as people think it is. So right now I'm just spelling it out, saying to increment I say I equals I plus 1.
Okay.
Okay, but we'll be using I plus plus very, very quickly. I'm having to pay close attention as I'm typing it, not to say I++, because that's how I would usually type it.
Yeah.
So now I'm going to say inside the body of this loop is going to keep going. This loop takes I on a voyage. So all this loop does is take I between the number 0 and in this particular case, the number 3. So the first time through the loop, I is 0. Second time it's 1. Third time it's 2. Fourth time it's 3, so on and so forth. As a programmer, I'm the one who gets to decide what do I do with that value of I. And what I'm going to do with it in this case is I want to output my string at that position. And I'll go ahead and kick it down the line here too. So each time through this loop, I'm going to output a character from my string and then press enter. So I should get the contents of my string M, I, K, E. 1 character per line. Make sense? Now, if I go up and I just change Mike to elephant and I change nothing else, now this loop will display all the characters in elephant because I wrote the loop generically to operate off of the length of my variable called name. I didn't hard code it to a 4 because that's how many characters are in Mike. I said variables hold values. I happen to know what it holds in this particular case, but as a programmer, we write stuff generically. So I want to go through and print out 1 character per line, all of the contents of a variable named name, whatever is in there. So there's my elephant. All right, makes some sense? All right, so your homework for, and I'll go ahead and save this and copy it just so you have some examples here. Homework for Tuesday is already up. It's going to have you work with some strings, write some loops that have you do things to strings. One of them, I think, has you reverse a string, which is going to be very, very, very similar to what we wrote there. You're just going to have to manipulate your for loop to go backwards instead of forwards. Something like that. All right. And it has you do some if statements dealing with printing out only the vowels or counting the vowels in a string, that kind of stuff. All right. Questions, comments, concerns, bribes?
Yeah.
So when's the first exam?
First exam will be around week 8. It'll be
Okay,
midterm. So as we get close to it, it'll either be during week 8 or probably the week after that, depending on whether we have a couple things to finish. But midterm.
okay, so it's be one of like week 8 and then week 16.
Yep.
Okay.
What is wrong? Oh,
Mm.
I have
Anybody online have a question?
Yeah.
Before I bail?
Yeah.
Go ahead.
it's kind of off topic. So in